advanced study, and he's going to talk to us about asymptotics of arithmetic eigenfunctions.
Thanks very much for the chance to speak again. So my starting point is going to be an old theorem of Hecke-Maass and Laplace, which tells you how big can a Laplace eigenfunction on a manifold be at a point. So just to introduce some definitions. So M will be a compact Riemannian manifold. Let its dimension be n. And this has a Laplace operator delta. So if you're not familiar with Laplace operators on Riemannian manifolds, just imagine, just think of the Euclidean Laplacian. This manifold locally looks like Rn, so this is some second order differential operator, which, you can think of locally as looking something like this, some of the second derivatives in some coordinate directions you pick. Okay, so because M is compact, then the space of L2 functions on M has a basis an orthonormal basis consisting of eigenfunctions for this Laplace operator. So I'll write the eigenvalue like this, and I'll assume that so there's lambda i's I'll call the frequency of the eigenfunction, and I'll assume that they're ordered increasingly. And it's known that these frequencies tend to infinity. Okay, so each fixed eigenfunction is just some, nice smooth function by elliptic regularity. I don't have much to say about them individually. What I'm going to be interested in is the asymptotic behavior as the frequency goes to infinity. So these functions are going to start sort of oscillating more and more, and I want to know asymptotic things about them, in particular how big can their peaks be. Okay, so the basic theorem about this is due to Hecke-Maass and Laplace, and it says that, assuming they're L2 normalized, it will be throughout this talk, the L infinity norm of these eigenfunctions is at most frequency to the power of n minus 1 over 2. Okay, so this I'm using the number theorist notation, not the analyst notation, so this means this is bounded by some constant times this, where the constant depends on the manifold. And this bound is actually sharp on the round sphere.
So the psi I normalized now L2 norm 1, right? So
Yes.
M is compact.
M is compact without alpha. Okay, so it's sharp on a round sphere, and also describe later what the functions saturating this bound on the sphere look like. But the first thing I want to say is, why this exponent? Why n minus 1 over 2? And there's a fairly simple kind of heuristic reason why it's that exponent. The one sentence answer is, this comes from a non-degenerate stationary phase integral in n minus 1 dimensions. So I'll expand on that a little bit, sort of explain that better. So let's just pretend our manifolds Rn for the purposes of explaining this. So I know that Rn does not have any square integral Laplace eigenfunctions, but we'll just kind of squint and make that detail go away. So let's think about how we could make an approximate eigenfunction on Rn that's, say, compactly supported and big at some point. So to start doing that, I'll write down an extremely simple Laplace eigenfunction on Rn. This is just a plane wave with frequency lambda, say traveling in the x1 direction. assume something like that. And then I'll take this plane wave and just average it under rotations around the origin. So I'll call that function phi lambda. So phi lambda of x will be the integral over directions in the n-1 sphere, e lambda of omega times the norm of x. Okay, so my point x, then phi lambda is obtained by taking my plane wave, just averaging it over the ball, over the sphere. Okay, so let's think about how big this thing is as lambda goes to infinity. Well, okay, you know, if we want to know the asymptotic size of this, say some fixed non-zero x, what are we doing? Well, we've got our x, we've got the, say in this case, the circle through x, or an R2. And so this is, you know, integrating the plane wave over the circle is some symmetry integral. And the integral is oscillating non-trivially, you know, over the upper half and lower half of the circle. And so, you know, because of that oscillation, that makes a negligible contribution to the integral. The only places that we need to care about here and here, which is where, you know, the integral stops oscillating, and we do stationary phase. We see this as you can show that these are non-degenerate critical points. And stationary phase says that the size of this is roughly, it's asymptotic to some constant, depending on x, times lambda to the n-1/2. And then, of course, at the origin, we have that this thing is size 1. Okay. So now what we're going to do, we're going to compactly, you know, do a smooth truncation to make this compact. So I'll take some function a and c infinity or Rn, and then, you know, you should believe me based on this that the L2 norm of this truncation is going to be asymptotic lambda to the minus n-1/2. I mean, assuming that I don't do something stupid like picking the zero function for this, let's say it's non-negative. Okay, so I can take this thing. This is going to be, you know, approximately a Laplace eigenfunction, and then I can L2 normalize it, multiplying by lambda to the n-1/2, so I'll get something which has a peak of size this at the origin. Okay. So you can think of this phi lambda as sort of a typical function saturating this bound of Vakuumowicz and Levitin. Although that's not so useful as it stands, because I haven't really told you very much about this function other than this and this. So I'll give you a little bit more information. So, you know, this phi lambda, right, it only depends on the radius, so I'll just write it as a function of that. So phi lambda behaves roughly like this. So we've got a phase, or rather two phases. We've got this amplitude, so this shows you the sort of lambda to the negative n-1/2 decay away from the origin. And this tilde here, this is the only point in the lecture at which this tilde will just mean I invite you to pretend that this function is actually this function. It's not like a formal asymptotic statement about it. Okay, but one thing I will do with this imaginary model about phi lambda is sort of look at the set of frequency directions it has. So what I mean by that, right, let's take some point in the plane. Now at that point, you know, if I look at phi lambda near that point, I see something that looks like kind of like a plane wave, maybe with a little bit of curvature, to sort of fit around the circle, traveling away from the origin. And I see something that looks like a plane wave traveling towards the origin. And if I do that at every point, draw the vectors pointing towards and away, and then at the origin, just take it from me that the correct thing to do is draw all the unit tangent vectors. I get this set in the unit tangent bundle of Rn, which I'll call F. And sort of a simple observation, but one that's quite important, the set F is invariant under the geodesic flow. Okay, so in other words, if I define GT to be the map on the set of unit tangent vectors that just says, okay, take a unit tangent vector, go along the line that generates the time t, like that, then GT preserves F for any t. Okay, and this is not a coincidence. There's a general principle that the high energy behavior of eigenfunctions is closely connected to the geodesic flow, the behavior of the geodesic flow. So this is often known as the correspondence principle. And one way you can think of it is, okay, well, Laplace eigenfunctions are sort of objects of quantum mechanics. If we're looking at high energy Laplace eigenfunctions, we're talking about high energy quantum mechanics. And we expect high energy quantum mechanics to look like classical mechanics. And the classical mechanics on the manifold is just the dynamics of the geodesic flow. Okay, so that's sort of Rn. So the second example I want to talk about where everything is really nice is the example of the round sphere. So the functions saturating this boundary. I mean, there are various functions that saturate this boundary on the round sphere, but the kind of typical ones that you write down are called the zonal spherical functions. Let's just say that. And if you want to imagine what one of these things looks like, just take the round sphere, pick any point, say the North Pole, and sort of take this fine end and imagine sort of melting it onto the sphere with the origin going to the North Pole. So it's got a peak there. It's rotationally symmetric around this pole, and then it's got a corresponding peak at the south pole. Okay. And then if we do this kind of frequency direction picture, the same as we did for Rn, what we get is, well, at every point we have the unit tangent vector pointing towards the North Pole and the one pointing towards the South Pole. And again, this is invariant under the geodesic flow, the set of directions. Now, something very simple that I just want to emphasize here, that this point, or I mean any point on the sphere, but this one in particular, has a very nice properties with respect to the geodesic flow. There's a time, namely the circumference of a great circle, such that any unit tangent vector pointing at this point comes back in that time and makes a smoothly closed geodesic. So, in general, I'll call a point like that a pole. So, we say point in the manifold is a pole if there exists some positive time t such that g of t, the geodesic flow at time t applied to v equals v for all vectors in, so it's all unit tangent vectors at p to n.
So let's see, these eigenfunctions all correspond to harmonic homogeneous polynomials on Rn, right? So
yeah.
We're
which ones are the ones you think the zone?
Let's see. I think. Which ones are these? You know, I don't know the answer. I don't know the answer to this off the top of my head. I know the answer for the ones that concentrate around a geodesic. But for those, they might just be sort of the powers of.
It must be functions of the transverse radius, distance from the axis.
Yeah, I think so. So it's probably, I mean.
But those don't tend to be harmonic, and it has to be confused.
Yeah, so
some
you have to take sort of harmonic.
You must have a
Some
power.
harmonic projection of that or something.
So
like
some
that.
function of the like the z direction, power of the z direction, and some power of the.
Something like that. Yes, I don't know the answer off the top of my head. Okay, so there's sort of a very nice generalization of this picture due to Sog and Zeldich. So what they show is that if a manifold has what I'll call a saturating sequence, so a sequence of eigenfunctions which satisfy the kind of reverse bound to our trivial upper bound, then there has to be some point which has very nice return properties for the geodesic flow. And so this is particularly nice, the result I get in the case of dimension 2 in a real analytic manifold. So I'll state that. So if we're in dimension 2 and our manifold M is real analytic, then it has to have a pole. M is real analytic and M has a saturating sequence, the most important part. This puts very strong restrictions on what M looks like. I mean,
So what does saturate mean in this context?
Oh, sorry. So yeah,
much
so
greater than you can't saturate that. So
no, I'm a number theorist in some twisted respect. So this doesn't mean much greater than. This just means greater than some constant times that. Okay. So in other words, you can't do any better than the Hekar-Maass letter time bound.
So, so that would say for a sequence of lambda going to infinity, though. I mean, so it doesn't for particular lambda. There's no constraint, right? You put the constant there. That's whatever constant works. But if you make a statement about a sequence of lambdas. So the statement would be there's a sequence of lambdas such that the ratio between those constants is between the infinity norm and the appropriate power of lambda is bounded above and below.
Yeah. So this is a very strong condition on the manifold. I mean, in particular, M has to have the topological type of a sphere, and then there's additional restrictions on geometry. So, for instance, you can have an ellipsoid with two axes equal, but two axes have to be equal. Things like that. And this condition is necessary. It's not sufficient, but it's sufficient for something weaker, namely that you can produce kind of little o of H quasimodes that saturate the Hekar-Maass level time bound, but that's sort of something more technical.
I'm sorry. The notion I know of a two manifold having a pole would force it to be non-compact. That would be a point where the exponential map is a diffeomorphism.
No. So a pole was this. So a pole was a point such that there is. I mean, it's like what any point on the sphere satisfies. There's some time at which every unit geodesic comes back and makes a closed geodesic loop. Every unit vector under the geodesic flow comes back and makes a smooth closed geodesic.
So every geodesic through that point is closed, is a statement. So that would be sole relative to that point, usual terminology.
Well, it's not just that every geodesic is closed, it's that they come back at the same time to be closed. Any other questions? Okay, where was I? Okay, so yeah, this is like a very nice example of links between, you know, saturation of the sup-norm bound and having nice geodesic flow properties. Okay, so now I'm going to switch to a context which is sort of as far from the round sphere and nice manifolds as possible. So now I'm going to talk about what happens in negative curvature. And so the geodesic flow on a negatively curved manifold is very chaotic. It's ergodic for loop measure in particular, and you certainly don't have poles like this. And so as a result, you know, based on the correspondence principle, we expect the eigenfunctions to also be doing chaotic things. So a really classic conjecture in this vein, even though it's kind of orthogonal to the question of sup-norms, is the quantum unique ergodicity conjecture, which is formulated by Riemannian and Stony. Thatcher. Oh, right, yes. So this says that if M is negatively curved, then the L2 massive eigenfunction spreads out uniformly over the manifold. So we write that as saying that if I take the probability measure, you know, obtained by taking the Riemannian volume form and multiplying it by the pointwise square of the eigenfunction, then this tends, in the weak star sense, to just the Riemannian volume. So that the L2 mass is spreading out evenly. So this is known, if you're willing to throw away a density zero subsequence of eigenfunctions, this is known. And it's actually known under the weaker hypothesis that the geodesic flow is ergodic. So this is the quantum ergodicity theorem due to Schnurren and Zeldich and Conte-Verdier. So you know the uniquely in here is the same kind of uniquely in when you talk about something being uniquely ergodic. You know, it's not just that this is an invariant measure; it's kind of the only measure that you get. And another important result from this conjecture. This, if you assume that M and these eigenfunctions satisfy some extra arithmetic properties that I'll introduce soon, this conjecture was proved by Lindenstrass. Okay, so that's a question about kind of the weak distribution of mass. But what about sup-norms?
So the sense of in which it converges is what?
Is sort of weakly in the sense of the kind of the distribution of mass.
The convergence of measures.
Yeah, convergence of measures. Okay, so you know that's an example of expecting and getting chaotic behaviour in negative curvature. But what about things like sup-norms? So in dimension 2, there's sort of a folklore conjecture that the sup-norms actually grow very, very slowly with the eigenvalue, so slower than any positive power of the eigenvalue. And in particular, we certainly expect a power improvement over the trivial bound. What we know is much, much weaker. So the best known bound on a general negatively curved manifold is just say a square root of log over the trivial bound. So that's, well, it is what it is. It's saving a root log. But where I get interested in, or sort of how I got into looking at all this stuff as a number theorist, is you can actually get a power improvement over the trivial bound if you make some extra arithmetic assumptions on your eigenfunctions and your manifold. So, how do you go about introducing number theory into this problem? Well, you have an assumption that you put on M, and you have an assumption that you put on your eigenfunctions. So the assumption that you put on M is that it's what's called congruence arithmetic. So the simplest example of such a manifold is the modular surface SL2Z, so the upper half plane quotiented by SL2Z. Now this is neither compact nor a manifold. It has this fundamental domain, so the strip between minus a half and a half and lying above the unit circle. And so we take this, we glue these two sides together by translation, we glue this line to this line by a rotation around I, and we get ourselves a non-compact orbifold. But I just invite you to forget about, just forget about both of those issues. Just pretend it's a compact manifold. It has lots of discrete spectrum. Okay. So this is the kind of prototypical congruence arithmetic manifold, but you can make lots and lots of examples. In particular, there are lots of, say, compact hyperbolic surfaces, which everything I'm about to say will work on just as well. Now, this M comes with a set of correspondences called Hekar operators. And to define them, it's natural to say that M is naturally bijective with a set of lattices in R2. So this is it's naturally bijective to lattices in R2 modulo the relation of homophily, so that's scalings and rotations. And the way this map goes, if I've got a point tau in the upper half plane, I send that to the lattice in C spanned by 1 and tau. And you can show that that map is, once you quotient by homophily here, that map factors through SL2Z, and in fact it gives a map from this quotient to these isomorphism classes of lattices. So once you think of M like this, then it's very easy to define these correspondences called Hekar operators. So for any natural number, we define this correspondence by saying that, well, if I take a point here and think of it as a lattice, then the set of corresponding lattices is just the set of all indexed n sublattices in this. So what this looks like, in terms of this picture is not too important. It's just I have my point, and this has a bunch of other points that map to it. Maybe something useful I can say is that if n is a prime, then this set of correspondences has p plus 1 points if you count things with the right multiplicity if you have collision. So generically, for a prime, a lattice has p plus 1 neighbours under this TP correspondence. Okay. Any questions about those definitions? Okay, so if you have a set with some correspondences, then those correspondences also act on functions on that set. Okay, so the way we do that, if I have a function, say, a continuous function on M, then I can define T and F at a point, so this Hekar operator acting on a function, I get by saying, let's take all the images of X under this correspondence and sum up F over those images. So I get matched non-functions by these Hekar operators as well. Okay, so these Hekar operators have some very nice properties. First of all, they commute. Second, they're self-adjoint for the L2 norm, and they commute with the Laplacian. Okay, so that means, I'd already kind of diagonalized L2 by a basis of Laplace eigenfunctions. Well, I can also assume that the basis I pick also consists of Hekar eigenfunctions as well. And so this is what we call a Hecke-Maass form. This is a joint eigenfunction with the Laplacian, and all of these operators Tn. Okay, so having introduced these objects, now I can state one of the main results on this problem, at least from my perspective. So this is a theorem of Riemannian and Sarnak, which states that we can improve over the Avakimovich-Levitin bound by a power if we look at Hecke-Maass forms. So if I have a hyperbolic surface which is compact and congruent arithmetic, which, remember, this just means it's got Hekar operators that work basically like these ones do. Come back and that congruent arithmetic. In Hecke-Maass forms satisfy sup-norm bound, which is a power Hekar, then trivial. So we can go from a half to 5/12, whatever. It's some, say, in the exponent. Okay, so you might look at this theorem and ask, well, okay, you've made this additional assumption on the eigenfunctions. Is this a big assumption? Like, is this kind of trivializing the problem? And I'd argue, as you might expect me to, that it's not such a huge assumption, and here's why. If we have a compact negatively curved manifold, the Laplace spectrum is expected to have really low multiplicities. Right? I mean, generally the only multiplicities you should see come from kind of obvious things like isometries of the manifold, things like that. And this is observed numerically as well. So if you believe that, then this additional Hekar assumption is really not a big deal, because you can take your favorite sequence of eigenfunctions, you take one of them, you look in the eigenspace, you write that eigenspace as the span of the Hekar eigenfunctions in it. You have this bound for the Hekar eigenfunctions, and so you get back a bound for the linear combination of them. And you have some small loss in terms of the dimension of the eigenspace, but if that dimension is small, you're happy. Okay. So any questions about that theorem? And I should add that this has also been proved for the non-compact example that I started off with. If you take square integrable things, and you can deal with non-compactness without too much trouble. So that's a very classic theorem on upper bounds. So what about lower bounds? Well, I'm going to say some theorems about that as well. And the most interesting thing about these results that I'm going to state is that this lambda to the epsilon conjecture that you can always hope to be true in dimension 2 fails in dimensions 3 and higher. So the first example of this is a theorem written in Sonic. So it says there exists a hyperbolic free manifold, a compact, in a sequence of Laplace eigenfunctions psi on n, which would be an L2 normalized, which grow like the power of the eigenvalue. And remember, the trivial upper bound here was just the frequency, so we're getting essentially like square root of the trivial bound in terms of their growth.
So just like I didn't explain what the much greater than symbol meant before, what does it mean when you put an epsilon, but even?
Oh, it just means so this is for any positive epsilon, and the constant depends on epsilon. So basically, it's sort of a half minus a small loss, which is as small as you want it to be. So the eigenfunctions here are really Hecke-Maass forms, and this thing is really arithmetic, but I don't have to tell you that. There's this example of a negatively curved thing with eigenfunctions that are concentrating in a really, really strong way, which is, I think, a very surprising thing. So this was extended to dimensions 5 and up by Donnelly. And he gets a lower bound of
Can you maybe give some intuitive explanation as to why it's surprising for a negatively curved manifold to have this? Because if the curvature is close to 0, what I mean by that is you can sort of take unions of torides, and so you can glue them together in an appropriate way. You could get these things quite easily.
So if the curvature is, this is a fixed compact thing.
Yeah. So you can envision taking a bunch of torides and pasting them together and having them shrink at some rate which involves sort of co-prime or like.
But how? Is that going? How are you going to produce a compact example?
They shrink fast enough, so somehow they.
But it's going to. Well, we can talk about this.
So why is it surprising? I guess I'm asking.
Well, just as I said, because it's generally expected that eigenfunctions on negatively curved things behave chaotically. The quantum unique ergodicity conjecture is widely believed, and the numerics in dimension 2 sort of don't really lead us to expect that this should happen.
Okay.
Okay, so I'm going to present two generalizations of this theorem and this theorem. So the natural setting that one would want to extend these results to is a class of manifolds with locally symmetric spaces. So these show up all of the place in number theory. For a number theorist, these are the places where orthomorphic forms live. besides being important in differential geometry.
Is it difficult to describe this group with równych sednach?
Which?
For each group, równych sednach. Gamma.
No, it's not hard at all. You just, I mean, they give a concrete example. They write down, I think it's the quadratic form. I think they take a quadratic form. I think it's that, or maybe with the 7 there. And gamma is the integral isometries of this quadratic form. And the point is also very concretely specified.
Maybe a finite, maybe a subgroup of that. I mean, you might expect to get over full singularity, or just to take that geometry.
Yeah, true. Yeah, maybe
Yeah,
that's just to get rid of the
Subgroup of finite index.
Okay. So to describe what symmetric spaces are, so the way you make a symmetric space is you start with so either a real semi-simple algebraic group or a semi-simple Lie group. And I'll assume that this doesn't have any compact factors because those just don't give us anything in the symmetric space construction. And then I'll choose a maximal compact subgroup K of G. And then if I take the quotient G mod K, this naturally has the structure of a Riemannian manifold. And it has the property that the neutral component of the isometry group of this is the quotient of G by its center. So G is essentially the isometry group of this thing.
Half simple is semi-simple?
Semi-simple. Yes.
Okay.
So a good example of this, for instance, all the hyperbolic spaces can be constructed like this. You take G to be SON1, which again, well, maybe if you take the quotient by the center, this is the neutral component of the isometry of the hyperbolic space. Another nice example is if you take G to be SLNR, then symmetric space, also that I can't describe what the Riemannian structure is, but as a set, it's naturally positive definite, symmetric, determinant 1, real matrices. And so you can put in a Riemannian structure on that such that this acts by isometries. Okay, so this S is some, like, it's non-compact, it's contractible in particular, it's diffeomorphic to Rn. And then if you take gamma into your lattice, you can form the quotient of S by gamma, and so that's what I'll call a locally symmetric space. So these things are the kind of natural things, manifolds to which one might try and generalize these theorems using the tools we have. Okay, so the first theorem I'll give is a generalization of this lower bounds result. Cool. So to state it, I'll introduce a definition. So we say a sequence of eigenfunctions on a manifold M is exceptional if their sup norms are grown like the power of the eigenvalues. Not that if they violate, say, lambda to the epsilon. So for some fixed delta, they satisfy that. Okay. So the theorem, this is joint with Farrell Brumley. Farrell Brumley myself. So I think it's most natural to state this for algebraic groups rather than Lie groups. So let G over R be a semi-simple R-simple algebraic group which is not split. Now, don't worry about this sentence too much if you don't understand it. After stating the theorem, I'm going to give a whole bunch of examples, but these are the technical conditions. Then there exists a manifold. So some locally symmetric space coming from the group G, which has an exceptional sequence. So, for example, you can take G to be SU in1 in at least 2, and so the manifolds you're producing are complex hyperbolic spaces, complex dimension at least 2. And you can also produce, say, quaternionic hyperbolic spaces, or if you take the rank 1 form of F4, you've got the octonionic hyperbolic plane. And then, I don't know, just to be fancy, you know, you can take, there's a real rank 4 form of E8. You can apply this theorem to that, so you get locally symmetric spaces of dimension 112 with sequences of eigenfunctions like this.
And how big is the exponent?
Sorry?
How big is the exponent of this exceptional sequence?
The exponent is not explicit.
That's positive.
Just positive. This comes from the fact that we're doing asymptotics of the trace formula, and this is all very involved. Yeah, it could have, yeah, it's computable in principle. So that's the kind of general lower bound theorem. And actually, I should say that if the key condition here is this one. I mean, this one we could drop, but the non-splitness is really essential. If you take a split group, then I wouldn't expect an exceptional sequence to exist. I would be about as surprised as if you found an exceptional sequence in dimension 2. Okay. The second result I want to state is generalizing the upper bound theorem of invariance and Sarnak. So, similar to here, I'll state it in terms of real algebraic groups. So let G over R be semi-simple. Quasi-split and not isogenous to SU n minus 1 for any n. then basically we can obtain a theorem about Laplace and Sarnak. We get some power improvement over the trivial upper bound. Hecke-Maass forms on any congruent arithmetic manifold associated to G. We have some positive delta, I can't tell you what it is exactly, but it's some power improvement over the trivial upper bound.
Do you expect delta to vary with G or with the actual manifold there?
Good question. So delta should just depend on, well, it should depend on G and maybe a little bit more. I mean, it shouldn't depend on, say, taking covers of M, for instance.
So is there actually a canonical lattice that you choose for each G, or?
Let's see. So in this theorem, I mean, we can handle any lattice. In this case, the question of exactly which lattices you can take is a little bit involved. But I wouldn't say there's like a canonical lattice that I take.
So it's not some algorithm that's related to a particular way that equalizes an algebraic group?
Maybe it's a little bit technical. Maybe we can talk about this a little bit. It's a little bit technical. Okay, so I think in the last.
No arithmetic conditions of this.
Oh, well, I mean. Oh, yeah. So certainly, if the manifold is chosen compact, then it's very easy to show that lots and lots of eigenfunctions exist. If it's non-compact, then we know that they do. This is a bit imperfect.
But this Hecke correct. In your example, look where so related to arithmetic nature of the group, and here it is just very general as it is still.
Well, I mean, the flavor of the Hekar operators is the same. I mean, that the Hekar operators wouldn't be there if we didn't make these arithmetic assumptions on the group that we're taking. So yeah, sorry, here gamma is assuming congruence arithmetic. Yeah, so I mean, it's implicit in saying it's a Hecke-Maass form, but I should have stated that.
In the last inequality, it depends on delta, or not?
Oh, the constant.
The constant, yeah.
Yeah. So the constant depends really on the manifold.
So it's but it's not like they even here zero where the constant becomes okay. The power of lambda.
Oh, well, I mean, there's no epsilon in my theorem because it's, Okay. Let's see. So I'm not sure if I have time to say anything about L functions, but I'll conclude by saying that just to give you like a little flavor of how these theorems are proved. The main idea is that the Hekar operators kind of act like an arithmetic version of the geodesic flow. So, just like in just the purely real analytic setting and the theorem of Solving-Zeldich, if you have a point that has very good returns properties there for the geodesic flow and here for the Hekar operators, then you can produce something that's big. And conversely, to show that nothing is too big, you want to show that no point gets mapped back to itself too many times by the Hekar operators. And so, yeah, that's kind of the path that you go down to both of these things. And the reason that we have these, say the non-splitness condition and the quasi-splitness condition here is that this issue of whether the Hekar operators can map a point back to itself lots and lots is related to whether the maximal compact subgroup of these groups is big. And so the kind of rough way of thinking about this condition is say not split means that the group has a fairly big maximal compact subgroup, and quasi-split means the maximal compact subgroup is not too big. Okay, so I think I'll stop there. Thanks very much.
Yes, dimension 2, there is some hidden relation to the Riemann hypothesis.
Yes. Yes, so the short version is this lambda to the epsilon conjecture would imply the Lindelof hypothesis for very special, for very special L functions associated with the Hecke-Maass forms. And conversely, this boundary by Sarnak implies a subconvexity bound, again for some family of L functions associated with the Hecke-Maass forms.
In high dimensions, is there?
In high dimensions, the picture is very complicated. But yeah, something like that is lurking in the background, certainly here. Not so much here, but definitely here.
Any other